talk this morning is by Shay, Gilpin, which is Continuum Covariance Propagation for Understanding Variance Lost in Advective Systems.
Thank you, Stephen. Hello, everybody. My name is Shay Gilpin. I'm a graduate student from the Department of Applied Math at the University of Colorado. And as Stephen said, today I'll be talking about covariance propagation and its connection to variance loss. Now, variance loss is this topic that is often discussed in data assimilation, especially with respect to the measurement update step and sampling errors. But what I'm going to do today is look at variance loss from a different angle in order to try to understand its root cause. And to do that, we will consider covariance propagation. So the equation for discrete covariance propagation that we'll be considering throughout this talk is given here. This is the method of covariance propagation we see in the Kalman filter, but this is also going on implicitly within 40 var schemes. So really, covariance propagation is an essential part of modern data assimilation. And what I'm going to show today is that if we propagate our covariances using this equation by conventional numerical schemes, this can actually be a source of spurious loss of variance. And fundamentally, this is going to be an issue with dynamics. And so, as mentioned in the title, we'll be considering this in the context of advective systems. And in particular, we'll be looking at the continuity equation, which we know represents mass conservation in our general circulation models, just as an example. So we'll let rho be our density over the sphere, and we'll take V to be our advection field. And if we were to implement this into a data assimilation framework, the first thing we would do is go ahead and discretize in time and space. So that generates our discrete state vector rho sub k. We propagate that forward in time using our propagation matrix M, which of course depends on our numerical discretizations. But really, once we have this discrete state vector, we can construct our discrete covariance matrix capital P. And then what falls out of that is this discrete covariance propagation equation given here at the bottom, which is the same equation we saw on the previous slide. Now, this approach of choosing to discretize first is the most common way to define covariance propagation in our data assimilation systems, and we really expect this to work. If we propagate our state using this propagation matrix, it works just fine. But what we'll see in this talk is if we choose to propagate our covariances in this way, it doesn't really work as well as we might think. And to understand why, we have to take a step back from discrete space and return to the continuum. And so to do that, we can use the continuum definition of our covariance and our state equation, and we can derive the continuum covariance evolution equation, which we have given here. And so by studying the covariance evolution equation, we can really obtain a fundamental understanding of how our covariance evolves in time. And we can gain important insights that may not be very apparent when just considering the discrete problem by itself. And so this idea of choosing to postpone discretization and study the continuum problem may seem like a very fine point, but actually what we'll see is the continuum analysis is crucial in understanding why the covariance matrix is evolving the way it does in discrete space when we use this equation here. And what we'll do is we'll use the continuum analysis by studying this covariance equation as a guide to interpret the results we see when we propagate our covariances numerically in our numerical experiments. And so to get a feel for this, we'll just use the continuity equation and do some numerical experiments. And so to do that, throughout this presentation, we'll be considering for our numerical results, the same one-dimensional continuity equation over the unit circle with this advection speed given here. And so what we're looking at in this figure is the trace time series, or the total variance, and how that evolves over time for 4 different initial covariances. So on the x-axis here, we have time. On the y-axis, we have trace, or total variance. And each of these 4 panels corresponds to a different initial covariance we've propagated. These initial covariances are constructed using initial standard deviation function sigma naught, an initial correlation function, which we take to be the Gasparian cone compactly supported approximation to the Gaussian. This correlation function is a function of a compact support length parameter, lowercase c, and that just allows us to adjust the initial correlation length of our covariance matrices. And so in each of these panels, what I've done is I've taken a compact support length parameter, which here will correspond to a short non-zero initial correlation length. And then as we move right in the figure, we shrink this parameter, which shrinks our initial correlation length until ultimately we get to a spatially uncorrelated initial covariance on the far right. In each of these panels, we're looking at 3 different curves. So the black curve corresponds to the exact trace as it evolves over time, and the 2 colored curves correspond to our numerical schemes that we use to propagate our covariances. So in orange, we have a Lax-Windroff scheme, and in blue, we have a Craig-Nicholson scheme. And right away, we can see that our numerics are not capturing the trace very well. If we start by looking at the exact curves, we see this abrupt change in the way that the trace behaves as we move from a spatially correlated initial covariance to a spatially uncorrelated initial covariance, and I'll explain why that is in a little bit more detail later. But if we look at our numerical schemes and say we start with the Lax-Windroff scheme in orange, we see that it's not capturing the total variance very well, and it's getting much worse as we decrease the initial correlation length. We know that the Lax-Windroff scheme is very dissipative, and we expect to see dissipation, but the total amount of variance lost, especially as we get to these short initial correlation lengths, is much larger than we would expect from dissipation alone. And so that indicates that maybe there's something else going on in our numerics that is causing this problem. And in fact, because Lax-Windroff is so dissipated, we're not actually going to look at it anymore throughout this talk, and instead we're going to focus on the Craig-Nicholson scheme here in blue. And so the Craig-Nicholson scheme seems to be doing okay, but is getting worse as the initial correlation length shrinks. And you could argue it's kind of approaching its own limiting behavior as we get to this spatially uncorrelated case on the right. Something else that we see is in a given panel, especially this one for c equals 0.15, there are regions in time where our numerical scheme here is under approximating the trace. So we see total variance loss. And then in the same panel, there are also regions in time where the numerics are over approximating the trace. So we see total variance gain. And so there's a lot going on in this figure, and looking at something as simple as the trace can kind of give us an idea that maybe there's something else going on besides dissipation that is causing this variance loss and gain. And as I had said before, to really understand this, we have to return to the continuum and study the continuum behavior. And so we can return to this covariance equation, and by studying it in the continuum, what we find is that along the surface where x1 is equal to x2, there is this discontinuous change in dynamics as our initial correlation length tends to 0. So as our initial covariance becomes spatially uncorrelated, there's a discontinuous change on the diagonal. Now you may be sitting there thinking that this is just some special case that mathematicians like to dwell on, but what I'll say to that is that this discontinuous change in dynamics actually has a significant impact on the way that our numerics try to handle this change and propagate the covariance in discrete space. And I would argue is not something that's very apparent when you just look at this problem in the first place. And so we can dive into this a little bit deeper. And what we'll do is we'll split this into 2 different cases. The first case we'll consider is when our initial covariance is spatially correlated. So we have some initial standard deviation structure, we have some initial correlation structure, and what we find is that along the diagonal, or along the surface where x1 is equal to x2, the evolution corresponds to the variance equation, which is given here. And this is exactly what we expect to see along the diagonal of our covariance. So this is the case where we have a spatially correlated initial covariance. We will see the variance evolving along the diagonal. But now let's consider the case where we have a spatially uncorrelated initial covariance. So this would correspond to a diagonal matrix in discrete space. In the continuum, we represent that with the Dirac delta function. And because now we're dealing with delta functions in the initial condition, we have to treat solutions to the covariance equation a little bit differently. And when we do that, what we find, interestingly, is that if the covariance starts out as spatially uncorrelated, it remains spatially uncorrelated for all time. And that evolution along the surface where x1 is equal to x2 corresponds to what we refer to as the continuous spectrum equation, or capital PC, which is given here. And what we can see by comparing these 2 equations is we have this change in dynamics. When we have a spatially correlated initial covariance, along the surface where x1 is equal to x2, we have evolution according to the variance equation. And then that dynamic shifts abruptly as we become spatially uncorrelated. We have evolution according to the continuous spectrum equation. And now in this case, it only really boils down to this factor of 2 in front of our forcing term. But this factor of 2 changes the dynamics between these 2 solutions and influences how our numerics try to handle this abrupt change when we propagate our covariances using these conventional methods. And so we can return to our one-dimensional example to kind of visualize what's going on. So here in the rest of these figures, what I'm going to do is I'm just going to extract diagonals from covariance matrices from this one-dimensional example and plot them at some fixed time as a function of space here on the unit circle. And so what we're looking at here is we're looking at the exact solution to the variance equation in black dashed and the continuous spectrum solution in solid black plotted at this final time capital T. And what we can see right away is this factor of 2 in their forcing term does impact the dynamics. These two are dynamically different. And so the question then becomes, if we propagate our covariances and we're shrinking our initial correlation length, how are numerical methods going to capture this abrupt change in dynamics? And that's where we really see this interesting behavior. And so that's exactly what we'll look at here. So these new curves that I've introduced are 4 different initial covariances that I've propagated forward in time using the Crank-Nicholson scheme up this time, final time capital T. And then I've extracted the diagonal and then plotted it along here along with our variance solution and continuous spectrum solutions. And so what we can see right away is that if we propagate our covariances using conventional means, they're producing diagonals that are smooth, but very wrong. Something else that we see is we're shrinking this compact support length parameter, or shrinking our initial correlation length. Our numerics are slowly approximating their own limiting behavior at the c=0 case, which contrasts what we see in the continuum because we expect this abrupt change. Now, something else we can do is I'm going to pluck out this blue curve, which corresponds to c=0.5, a very short but non-zero correlation length, and look at that in comparison with the variance and continuous spectrum solutions. And so that's exactly what we're looking at here. So we're comparing this numerically propagated diagonal along with the variance and continuous spectrum solutions like we just saw, but now at 2 different times. And what we can see here is that our numerically propagated diagonal for this short non-zero correlation length is better approximating the continuous spectrum solution rather than the variance solution, which is what it should be approximating. And so if we didn't perform any of this continuum analysis, we didn't know that the continuous spectrum solution existed, we would just assume that this is just numerical dissipation. Our numerics are just highly dissipated, and that's why we're seeing this significant amount of variance being lost. But in fact, it's our numerics actually approximating a different problem entirely. And so this really highlights that this is more so a dynamics issue rather than just dissipation alone. And so to summarize what we've just seen is we have this contrasting behavior between the discrete covariance propagation and what we expect from our continuum analysis. Our numerics are gradually approaching their own limiting behavior as the initial correlation length shrinks, rather than just this abrupt change in dynamics that we expect from the continuum. And then this last point, which we just looked at, is for these short initial correlation lengths, our numerics seem to better approximate the continuous spectrum rather than the variance. And we can exploit this last point to try to understand variance loss in the context of this problem. And so if our numerics are better approximating the continuous spectrum, it makes sense to then look at the difference between the variance and the continuous spectrum in order to try to quantify variance loss. And the advantage of this is then we can move back to the continuum and study the dynamics there, which will then help us interpret what we're observing in our numerical experiments. And so when we do that, we can actually derive this very nice relationship between the variance and the continuous spectrum solutions. And they all hinge on this factor m here, where m evolves according to the continuity equation with an initial condition of 1. And this you can just derive straight from the PDEs for the variance and continuous spectrum. And so what's really nice about this relationship is it allows us to connect these physical concepts of mass convergence and divergence to the variance loss and also the variance gain that we see in our numerical results. So if we're in a region of mass convergence where the scale factor m is greater than 1, we know that the variance is going to be larger than the continuous spectrum. So if our numerics are better approximating the continuous spectrum, we would expect to see variance loss in these regions of mass convergence. And then the converse is true in regions of mass divergence. We would expect to see variance gain in our numerical experiments. And again, if we look at this equation for m, these regions of mass convergence and divergence only depend on the advection field. And so we can get a feel for this by going back to our one-dimensional problem. And what I plotted here is, again, we're just looking at the solutions to the variance equation in black dash and the continuous spectrum solution in solid brown at these 2 different times. And what I've highlighted in gray is this region of mass convergence. And what we'll see is that this region changes in space and time, but we have both mass convergence and divergence. And that comes from the fact that m satisfies mass conservation. And so that is emphasized in this figure. We'll look at this case again for the short correlation length. And what I want to point out is if we compare our numerics here in blue to the true solution, the black dashed curve, we see regions of variance gain where our numerics are over approximating it, and then regions of variance loss where our numerics are under approximating. And so we can quantify this really by inaccurate variance propagation. And that's also emphasized by this additional curve here in green, where what I've done is I've propagated the variance independently using Crank-Nicholson, and that is doing pretty well. And it emphasizes the fact that propagating our covariances independently, propagating our covariances using traditional means produces diagonals that are very inaccurate. And so I will wrap this up right now. But what I would like to do is shift our mindset away from this idea of variance loss. Yes, I understand it's very problematic in data assimilation, but what I've just shown is that we see both variance loss and variance gain. And together we can really describe that by inaccurate variance propagation. And it's inaccurate because we've studied this behavior in the continuum. We know how it should be behaving, and it's not behaving as well as we might think. And so just to wrap this up, there's a lot more that can be done with this problem. We can extend this to higher dimensional problems, systems of equations that are more relevant to numerical weather prediction. We can explore alternate means of covariance propagation. But what I want you guys to take away from this is that our conventional means to propagate the state work just fine. But using the same methods to propagate the covariance are not working as well as we might expect. And so this may be a good time to rethink how we're propagating our covariances in our data assimilation schemes. So thank you for your time. I apologize for going over. My email is here, and I'm happy to take questions or discuss offline.
Cool. Thank you for a very good talk. So I've got the questions are starting to come in now. So first one from Javier is, are there more complicated discrete numerical schemes better equipped to cope with this problem? And I was also sort of appending to that. I mean, have you considered semi-Lagrangian methods, which are sort of more preserving methods?
Yeah, so that's something that that's a good next step to take. I think that's something that I've not looked into. Really what we tried to focus on is, it was a very exploratory thing at the beginning, just to try to see really if what we were observing in terms of variance loss was more so due to the dissipation of the numerical scheme. But what we found as we kept exploring, even with just these simple, finite difference schemes, that it's really a dynamics issue more so than anything else. And so I think a good next step would be exactly that, to be explore, other means of solving the covariance equation to see if maybe, finite differences works, but it's not necessarily the best. And so, yes, that is a good next step to take. I've not done it, but it's definitely something to think about.
Cool. So the next question is from Mohar. Technically, P equals MPM transpose plus Q. Shouldn't model error covariance Q account for some of the dissipation or underestimation of P?
Yes, okay, thank you for your question about that. So in our case, we were assuming that we did not have any model error, that what we had was truth. And that, of course, makes the problem a little more complicated, especially when you're introducing that Q term. I would argue that yes, I think the Q term would definitely take some of that into account. But I think with what we've shown is that the amount of errors that we're seeing is going to be much larger than what may be captured in that Q matrix is kind of what I would think. So what we were trying to do is really focus more on the dynamics of the problem. And then, of course, again, the next step would be to then introduce, this model error term, which I think may capture some of it. But I think, it's a dynamics issue more so than anything.
So the last two questions are kind of similar to each other. Is like, can you comment on how this would port over to when we use ensembles? This is from Lars. Then we have a sort of continuum, don't we? And then Chris Snyder says, consider ensemble DA techniques. The numerics appear at the level of model dynamics. Is there a link between model numerics and your covariance propagation results?
Yeah, so I'll go back really quickly to this slide because I think it's nice to have. So in ensemble schemes, really, we're approximating this equation because we're approximating our covariances using our set of ensembles. And so indirectly, this is going on, we're approximating it. I would think that because we're propagating our states using these model dynamics, that I think you would still see this. I don't have a definite answer. I wish I could give one. But my hunch is that you would still see this same type of dynamical issue. But that's definitely something, again, I would like to look into because it's very important within the context of what we do, because we do a lot of ensemble stuff. And so a good next step, yes, would be to look at it. But my hunch is that we would still see this type of problem. The question is really how to diagnose it, because it's not as explicit as you do, say, in a Kalman filter. You have to kind of think about it a little bit differently because now you're dealing with ensembles.
Okay, thank you. So this